Hello, this is a review session for 110 acoustics, where we could go over units 1, 2, and 3. Unit 1 being frequency, wavelength, and speed of sound. Unit 2 being decibel and intensity. And Unit 3 being complex sounds, such as speech versus noise. What we could do is, since I have no attendees here, I will go over some of the practice questions that we had and that I may have sent to you earlier. Maybe I did, I can't quite remember. But why don't we go over a couple of practice questions that cover stuff from each of the units. Let's just check this out and see what it is. Okay, I'll share screen and say share. And make that guy smaller, go to my Microsoft Word notes, and I can see over on the bottom right, I've got some practice questions. Now, looky, okay? What we have here, besides a failure to communicate, what we've got here, look at question number 1. Calculate the frequency of a 4 millisecond period. Now, what is 4 milliseconds? If you look at 4 milliseconds, 4 1/1000ths of a second. So that would be 0.004 seconds. Okay? So if that's the period we're talking about, how do you find frequency? Well, frequency is equal to 1 divided by the period. So if you take that further, you say frequency is equal to 1 divided by 0.004. And then if you take your trusty dusty calculator, okay, which you might be able to see on the top right of the screen here, and you do a 1 divided by 0.004, you will end up with 250. So I guess your frequency is equal to 250 hertz. Frequency is 1 over the period. Period is 1 over the frequency. Those are the first 2 sets of formulas to keep in mind for this particular half of the course. Those are the first 2 formulas. F is 1 over P. P is 1 over F. Let's try this. Try the next one. Over to number 2. Now calculate the wavelength. Well, what did we say wavelength was? Wavelength is equal to speed of sound over frequency. Okay, so if that's what it is, what's the speed of sound? 340 meters per second divided by the frequency, 250. And what is that? Get your calculator out. 340 divided by 250 is equal to 1.36. 1.36 what? 1.36 meters. Because you've got to keep meters over meter, 340 meters per second. Okay? And if you wanted to try it in good old feet, why don't we try that? Okay, let's try that. Go boom, 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 boom. 1,130 feet per second divided by 250. Again, get your calculator out. Let's figure out what it is. 1,130 feet per second divided by 250 is equal to 4.52 feet. So that would be equal to 4.5, basically 4.5 feet. Okay, 1.36 meters is about 4.5 feet. Because what's a meter? About a yard. A yard is 36 inches, a meter is 39 inches, so basically 1 1/3 meters is about 4.5 feet. Okay, so there you have it. You're looking right at this square. It's just slain and pimple. Keep it simple. Okay, look at the next one, number 3. Calculate the frequency of a 10 millisecond period. All right, by the same token, remember F is equal to 1 over P, so F is equal to 1. Now, how do you draw 10 milliseconds? Okay, 10 milliseconds. What is 10 milliseconds? 10 milliseconds you'd be doing, okay? 0.010 second. 10 milliseconds, 10 1/1000ths of a second. So if frequency is 1 over period, like you see here, then you'd say frequency is equal to 1 divided by 0.010, and that would be equal to, get your calculator out, 1 divided by 0.010 is equal to 100 hertz. Now calculate the wavelength. Well, wavelength is speed over sound. That's what you got over here. So speed of sound is 340 meters per second divided by 100. So what would that be? 340 divided by 100, 3.4 meters. 3.4 meters. Or if you did it in feet, 1130 feet per second divided by 100. 11.3 feet. 3.4 meters is 11.3 feet. Works out for me. Now, number 5. Calculate the period of 8,000 hertz. The period of 8,000 hertz. Now remember, F is 1 over P, P is 1 over F. So the period, what does period mean? The length of time it took for one cycle. So let's look at the period of 8,000 hertz. F is, or period is 1 over frequency, so 1 divided by 8,000 hertz is equal to 1 divided by 8,000 hertz is equal to, wow, that's a weird number. Here we go. 0.000125 seconds. Yikes. I got too many zeros in there. Need one less zero. 0.000125 seconds. Well, that's what it is. I didn't make it up. Okay. Now calculate the wavelength of 8,000 hertz. Well, wavelength equals speed of sound over frequency. So 340 divided by 8,000 hertz is equal to, let's find out what that is. 340 divided by 8,000 hertz. Whoa, okay. That is going to be 0.0425 meters. 0.0425 meters. Let's make it more common sense for us people who live in the States. 1,130 feet per second divided by 800 hertz, 8,000 hertz is equal to, let's try that, 1,130 feet per second divided by 8,000 hertz. That is going to be 0.14125 feet. So it's just a little bit over 1/10 of a foot. Okay, getting short. All right, maybe that's about 1.5 inches in length. Talking small. Calculate the period of 125 hertz. Period is 1 over F, so 1 divided by 125. Let's try that. 1 divided by 125 equals 0.008 seconds. Well, I guess that's going to be 8 milliseconds. Same thing. You could call that 8 milliseconds. I'll just make or here. Or, so 1 divided by 125 equals 0.008 seconds or 8 milliseconds. Fine. Good stuff. Now calculate the wavelength. Wavelength of 125, so 340 meters per second divided by 125. There we go. Have a sneeze. 340. 340 divided by 125 is equal to 2.72 meters. 2.72 meters. You want to do it in feet? 1,130 feet per second divided by 125 equals 1,130 feet per second divided by 125 is equal to 9.04 feet. Now look at that. A 125 hertz tone is 9 feet long. Trippy, huh? If you went to 250 hertz, you went up 1 octave. Let's say if you went to 125. If you're at 125 hertz, and I'll stop sharing for a second here, okay? If we went to 125 hertz, you're at 125 hertz, it's 9 feet long. What happens when you go up an octave? Now you're 250 hertz. Well, what's 125 times 2 is 250. I guess you'd take the period of the 125 and you'd divide that by 2. You'd make it shorter. Remember, frequency is inversely related to period. Frequency is also inversely related to wavelength. So the higher the frequency, the shorter the period. The higher the frequency, the shorter the wavelength. So 125 is higher than 250, or I should say 250 is higher than 125, and 250 is double 125. And if 125 hertz is 9 feet long, here 9 feet long, okay, then 250 is going to be half of 9, 4.5 feet long. And 500 hertz is going to be not 4.5 feet divided by 2. Well, what is that? 4.5. 4.5 divided by 2 equals about 2.25 feet. And 1,000 hertz is going to be 2.25 divided by 2. 1,000 hertz is going to be 1 foot, a little over 1 foot, 1.125 feet. And 2,000 hertz, I'll just divide that by 2, is going to be 0.5, my calculator needs a light here, 0.56 feet. And 4,000 hertz is going to be that divided by 2, 0.28. And 8,000 hertz is going to be half of that. So as the frequency goes up, the period gets shorter in time. Period. Always think of the watch. What was the length of time for one cycle? And as the frequency went up, how about the physical wavelength? That also got shorter. Cool. Share a screen. Let's look at our practice question again. Here we go. Work our way down the page. Now you got these weird guys sitting in the middle here. Now we're going to look at this from another angle. Okay, look at the following questions for the sound waves below. And if you look at these sound waves, you'll see a top one here and a bottom one over here. So question number 9 is asking you, what's the period of the top sound wave? Well, time is on the horizontal, amplitude is on the vertical, also wavelength is on the horizontal, amplitude is on the vertical. But here we're talking, what would be 0.002 in terms of things? These would be seconds, 0.002 seconds, 0.004 seconds, 0.006 seconds, and so on. So we're looking at time here. And we're not even asking wavelength, so we're just looking at period and frequency. Look at what the questions are saying. Good. So what's the period of the top sound wave? Well, what was the length of time it took to complete one cycle? 0.002. So you'd write 0.002 here. And what? Seconds. Or 2 milliseconds. Either one. Now, what's the frequency of the top wave? Well, F is 1 over P. So F is equal to 1 divided by 0.002, which is equal to, trusty dusty calculator, 1 divided by 0.002 is equal to 500 hertz. Good. What's the period of the bottom wave? How long did it take to complete one cycle? 0.004 seconds, or 4 milliseconds. Move on over. Did you get number 11? What was the length of time to complete one cycle? What's the frequency of the bottom wave now? Okay, how now, brown cow? Okay, what's the frequency of the bottom wave? You know what the period is, so it's going to be 1 divided by 0.004. Now what would that be? 1 divided by 0.1 divided by 0.004 is equal to 250 hertz. And that makes sense. Okay, 250 is half of 5, okay, is half of 500. And looky, the period is double the length as well. So one cycle of the bottom, how many took place in the top? 1, 2 took place at 0.004. So obviously the top wave is higher in frequency, and its period was double, so the frequency's got to be double. Okay? Well, the period here is double, so the frequency has to be half. The period here is half the period of the bottom one, and so the frequency has to be twice as high. Period and frequency are inversely related. What other questions do we have here? Does this go on? No, it's done. Good. I'll close this one here, and it's going to say, do I want to save it? No, I don't want to save it. Okay, we'll leave it. But now we'll go to our notes. So make sure that you have a good handle on that guy right there. Okay, don't worry about the second half of the page. Make sure you have a handle on 2 ways to represent sound. Sound can be represented as a sound wave or on a spectrum. And know the axes of a sound wave as opposed to a spectrum. Okay? Sound wave, horizontal is time, vertical is amplitude. Spectrum, horizontal is frequency, vertical is amplitude again. Okay? Good. And there are advantages and disadvantages of each one. Again, waveform, time and amplitude, spectrum, frequency and amplitude. Amplitude is spoiled. It's represented on the vertical of both of these. But now you've got 2 ways to show sound, because sound takes place in 3 dimensions: frequency, intensity, and time. And a piece of paper only has 2 dimensions. So I'm going to need 2 ways or 2 kinds of graphs to show 3 dimensions. So here it is: amplitude, frequency, and phase. Okay, those are the 3 dimensions of sound. And then this set of formulas was next. So you had F is 1 over P, P is 1 over F. That's set number 1 formulas. Set number 2 formulas is this one: wavelength versus frequency. And that's what we did in our practice questions. We worked through 2 of the 3 formulas that we've covered so far. The third one is intensity in the decibel, but we'll get there in just a minute, okay? Let's finish this puppy off right here. Wavelength versus frequency, and put stars by these guys, okay? Wavelength is speed of sound over frequency. And then I give you an example. For an example, 5 is equal to 10 divided by 2. Okay? And when you do such a thing, you can also just say 5 over 1 is equal to 10 over 2. Okay? Whenever you see questions like this, always, if you have only one number on one side of the equal sign and you got 2 numbers on the other side of the equal sign, always put a 1 underneath the first one here. So 5 over 1 is equal to 10 over 2. And now you can flip the formula around. You can do this: frequency equals speed of sound over the wavelength. For example, 2 is equal to 10 divided by 5. Or 2 over 1 is equal to 10 over 5. Same thing. All we're doing is flipping the formula around. And that's useful, because sometimes I might be saying, you know what the wavelength is, now you got to find the frequency. And sometimes you know what the frequency is, now you got to find the wavelength. So either way, here's the trick to remember. Speed of sound is always on the top. Okay? 340 is always on the top, or 1130 feet per second is always on the top. Wavelength equals speed of sound over frequency over here, and frequency equals speed of sound over wavelength. Either one. Okay, speed of sound is always the puppy on top. And I'm never asking people to look at the third one. But if you did, 10 is equal to 2 times 5. All we're doing is flipping things around. So now you've got a formula here, and don't worry about the word lambda. That's just some Greek word used often in physics to represent wavelengths. So now you've got 100 hertz. Wavelength over 1, okay, equals 340 meters per second over 100. That's the frequency. So you want to know what the wavelength is? Well, 343 divided by 100 is 3.3 meters. Or in feet, wavelength over 1 is 1130 feet per second divided by 100. And when you do that, you end up with 11.3 feet. And then for 250, 343 meters per second. If you did 343 or 340, doesn't matter to me. 343 is exactly at 20 degrees Celsius. And you're wondering what the hell is that? Well, multiply by 2 and add 30. You'll get Fahrenheit. 20 degrees is a nice end of spring day, early summer day for Canada. 20 degrees Celsius is nice. Let's do it. What would that be? 20 times 2 and add 30. 20 times 2 is 40, add 30 is 70. 70 degrees Fahrenheit. A nice, coolish summer day, warm spring day, 20 degrees. A real nice summer day in Canada is about 25. What's that? 25 times 2 is 50, add 30, 80. 80 degrees. That's a pleasant, I like that. I know people down in Missouri are hitting 95, 100s quite often. That's a little on the warm side for me. I'd rather not. But at any rate, here's another thing, important concept for those who fit hearing aids. Lows bend, highs bounce. Remember all that? Cool. Why is that important for hearing aids? You should have written in your margin there, feedback, the whistle. High frequencies bounce out of the ear canal. Speed of sound. There's something else. So here's your speed of sound, exactly 343, or, it just gives you an idea. Those are good handles to have. I would put those in your pocket, okay? Put a star by that. Don't worry about speed of light. That's for physics, but I just give that to you for fun, okay? This one you need to know. Speed of sound is 4 times faster in water. It's 14 times faster in metal. You need to know this too. Speed of sound depends on the density and the stiffness of the medium through which it travels. Remember, density is equal to mass, elasticity is equal to stiffness, and both of those affect sound going through. Both of those make the medium act as a filter. Okay, certain things are going to get through and other things are not going to get through, but nonetheless, don't worry about inversely blah 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 blah, and don't worry about blah 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 blah. But if you say to yourself, okay, if things are more dense, basically what this means here is that the more dense something is, the slower sound goes through it. The more stiff something is, the faster sound goes through it. These are just talking the speed of sound, okay? Now remember, in any one medium, all frequencies travel the same speed. So in air, all frequencies travel the same speed. In water, all frequencies travel faster, but they all travel the same speed. In metal, all frequencies travel even faster yet, but they all travel the same speed. The more dense something is, the slower sound is. The more stiff something is, the faster sound travels. So fluids and metals, yep, they are more dense than air. So why does sound go faster through these media? You'd think they'd go slower. Well, we forget to look at the elasticity. Steel is also a lot more stiff than air. And the elasticity of steel is 230,000 times greater than that of air, whereas the greater stiffness of or density of steel is only 6,000 times that of air. So the greater elasticity outweighs the greater density. That is why sound goes faster through steel, even though it is more dense. All right. Remember this too. Speed of sound, as I said, has no relation to the frequency. In any one particular medium, All frequencies travel the same speed. The Doppler effect happens below the speed of sound. Sonic boom happens above the speed of sound. I won't go into those now as a review, but you should look at your Lassen-Woodford for an explanation on some of that, because it's pretty good. Sound fields are important to know because you are, as an HIS, are going to be looking at this. Okay? A free field is a room that has no vacuum at all. No vacuum, no reverb, no echo at all. Free field means the sound just travels. A free field would mean like you were 1,000 feet up in the air and you made a sound and there was no walls, nothing for the sound to bounce off of. Well, it's pretty rare. Okay, an anechoic room is the closest you can make to that, a real sponge layered room where there's no reverb or echo. What's a reverb or echo? A reverberation is a very short echo. Okay, an echo is when the time delay between the original sound and the reflected sound is greater than 1/10 of a second. A reverberation is when the difference between the original and the reflected sound is less than 1/10 of a second. Enough on that. Next. Standing waves, anechoic rooms, important to know. Okay, sound treated rooms, very different. Okay, that's what we use to test hearing. Think of water resistant as opposed to waterproof. This is an important concept as well. You're going to have this over and over and over again. Impedance equals resistance plus opposition. In any particular object, there is resistance to the passage of sound and opposition to the passage of sound. Okay, so we're no longer talking speed of sound, we're talking something different. Okay, impeded means opposed. And the resistance in any object is like simple friction. And the resistance to frequencies of sound is going to be equal to all frequencies of sound, for all frequencies of sound. So in a cup or in a metal rod or in a railroad track or God knows what, the resistance to the passage of sound is equal for all frequencies. There will always be some resistance, otherwise sound would travel forever. And it doesn't, it always dies out, obviously. But in addition to resistance, there's also opposition. And the opposition is sometimes called reactance. And the reactance or opposition can be broken down into two parts: opposition due to mass, opposition due to frequency. So opposition due to mass, what is that? Mass, think of a locomotive. Does it like to be jiggled? No. Mass opposes high frequencies, doesn't like them. It opposes them. Stiffness does the opposite. Stiffness opposes lows. So if mass opposes highs, what does it like? Mass likes lows. So mass opposes highs, it resonates with lows. Stiffness opposes lows, it resonates with highs. Remember, opposition or impedance is an upside down smile is resonance. So impedance equals resistance plus opposition. And remember, opposition has two children, opposition due to mass and opposition due to stiffness. Good. Resonance being the opposite, look at how far we've come. And now we get to the bottom of Unit 1. And here we look at quarter wave resonators. And in complex sound, we talked about the throat, Unit 3. In this unit, we talked about the ear canal. Both of them, like a cup, are quarter wave resonators. Cylinders closed at one end, open at the other end. Okay? So remember that. Quarter wave resonators are unique individuals because they tend to resonate with sounds that are 4 times their length. Okay, not a quarter their length. I'm going to ask this, so don't mix it up, okay? If a cup is 1 inch long, it's going to resonate with sound waves 4 inches long. If a cup is 1 foot tall, it's going to resonate with sound waves 4 feet long, okay? So, 2 examples of quarter wave resonators in our field are the ear canal and the vocal tract, your throat. The outer ear canal is 2.5 centimeters long. Speed of sound in air is 343 meters per second. So your ear canal is going to resonate sound with sound waves that are 4 times 2.5 or 10 centimeters. And what's 10 centimeters in meters? A tenth of a meter. And you got to keep dealing with meters to meters because you're talking about the speed of sound being 343 meters per second. So even though 2.5 centimeters length of an ear canal times 4 is 10 centimeters, I have to convert that 10 centimeters to meters so that I'm dividing meters over meters. So 343 meters per second divided by 0.1 meter. And when you do that, look what you have here. Here it is. Frequency is wavelength. Frequency is a wavelength, or I should say frequency is speed of sound divided by wavelength. Remember, wavelength is speed of sound divided by frequency. Frequency is speed of sound divided by wavelength. So here we're using that formula that we covered earlier, and I move on up to here so you see it. So instead of doing wavelength as speed of sound over frequency, now we're doing frequency as speed of sound over wavelength. We're just asking a different question because now we know what the wavelength is. Our question is, what is the frequency? So let's do it. Bottom of your page. So frequency is speed of sound over wavelength. So frequency over 1 is speed of sound divided by the wavelength of 0.1 meter equals 3,400 hertz. So really the resonance of your outer ear canal would be 3,400 hertz. But remember from 120 anatomy, your ear canal is made of flesh and bone. And so that it's not a steel cup or a glass cup. So that resonance is going to be spread. And that resonance is generally spread from about, and I'll write this down, from about 1,500 hertz out to about 4,000 hertz. And the peak resonance is going to be about 2,700 hertz. Okay? Remember those numbers. It's important. And how many decibels is that going to give you? About 20, 25 extra. And why do you have that? The better to hear the high frequency consonants, my dear. Okay? Your outer ear canal acting as a quarter wave resonator. And this we touched upon in anatomy 120 when we looked at the physiology of the ear. Here we're looking at that same physiology in terms of acoustics. Same story. Now, helium speech. This is something else that we covered in Unit 3. Okay? And we're looking at it in Unit 1. And when you look at it, why is helium speech high-pitched? Well, your vocal tract, your throat, from your larynx to your lips is 17 centimeters. Speed of sound in air is 340 meters per second. So it's going to resonate best with sound waves 4 times as long. 4 times 17 is 68 centimeters. So frequency is speed of sound over wavelength. Frequency is over 1 divided by 3, or is equal to 343 meters per second divided by 0.68 meters, because 68 centimeters is 0.68 meters. We got to divide meters by meters. So 343 divided by 0.68, 500 hertz would be the resonance of your vocal tract. Now let's inhale some helium. Helium, remember, though, is less dense than air. That's why helium balloons float up. They go up, okay? Because they're less dense than air. So what happens? The more dense something is, the slower sound goes through it. The less dense, faster sound goes through it. So sound travels through helium at 927 meters per second. F over 1 is equal to 927 divided by 0.68. And when you do that, you get 1,362 hertz. No wonder your voice gets higher on the helium. Okay, close this unit down. Next, make sure that you've got intensity and the decibel down. And remember the formulas here. So you've got 2 sets of formulas now. F is 1 over P, P is 1 over F, and Frequency is wavelength over speed of sound. Wavelength equals, I should say, frequency is speed of sound over wavelength. Wavelength is speed of sound over frequency. That's your second set of formulas. And now we're looking at your third and your last. Okay? Force is energy. Remember this one. Pressure is force over an area. So X amount of pressure on your, or force on your hand, on your cheek, is a lot less pressure than the same force converged over your fingertip. And that has lots to do with your middle ear, because that's what your middle ear does from Anatomy 120. Sound hits a big eardrum, and that same force gets converged onto the footplate of the staypiece. Pressure is force over an area. So what scientists did was they measured the softest pressure it took for a normal hearing human adult to hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears. And always remember that sentence. There's 3 pieces to it. Okay? First is the 1,000 hertz tone. Second is the distance from the speaker. And thirdly is the listening condition with 2 ears. And they called that pressure, whatever that pressure was, and they found out what it was. It was 0.0002 dynes per centimeter squared. And they called that pressure 0 dB SPL. Remember that. That's the cornerstone. Some scientists look at sound intensity in terms of power. And if you looked at power, what's the softest sound power it took for an average adult with normal hearing to hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears? Okay? In terms of power, that was 10 to the minus 16 watts per centimeter squared. So the smallest you could hear, 10 to the minus 16. The largest you could tolerate, okay, 10 to the minus 4. And there's a typo here. It says 10 to the minus 16 is larger. That should read smaller. 10 to the minus 16 is 1 trillion times smaller than 10 to the minus 4. The largest you could tolerate was 10 to the minus 4. The smallest you could hear was 10 to the minus 16. What's the difference? 10 to the 12. 10 to the minus 16 versus 10 to the minus 4 is 10 to the 12. So the range of our hearing in terms of power would be 10 to the 12. And that's quite a lot. 10 to the 12, it's a 1 with 12 zeros behind it. 3, 6, 9, 12. You have first 1,000 or 1,000,000 or 1,000,000,000 or 1,000,000,000,000. So in terms of power, the range of our hearing from softest to loudest is 1,000,000,000 to 1. And now we move to pressure because the ear works as a pressure unit. We're thinking more in terms of force received on something, like a microphone or an eardrum. So we prefer pressure. And the softest pressure is 0.0002 dynes per centimeter squared. And the greatest pressure is 200. And 200 is 1,000,000 times larger than 0.0002. So the range of our hearing in terms of pressure is 1,000,000 to 1. But please don't think that this has anything to do with actual differences. Remember, freezing is freezing is freezing, boiling is boiling is boiling. And the difference between the two is the same whether you're talking Celsius or whether you're talking Fahrenheit. If you're talking Fahrenheit, freezing is 32, boiling is 212. Come to my side of the border, freezing is 0 and boiling is 100. Well, ice ponds freeze over at the same temperature in Canada as they do in the US. We just call it 0. You guys call it 32. So boiling is going to hurt your hand if you put your hand where the egg is boiling, regardless of what side of the border you're on. Okay, so boiling is boiling is boiling. It's just that your thermometer has more degrees in it. The distance between the top and the bottom is the same, but our thermometer here has the same length. It's just that the degrees are thicker. That's what we mean by power versus pressure. So in terms of pressure, the softest is 0.0002, the top is 200. That's a million times difference. Okay, in terms of power, the softest is 10 to the minus 16 and the greatest is 10 to the minus 4. There's a trillion times as much there. But please don't think that has anything to do with the greater difference. It's just that power equals pressure squared. The thermometer of power has skinnier degrees than the thermometer of pressure. Okay, having said that, now back to share. Back to share. So we move on down. And you're looking at all these numbers. Doesn't matter. Flow down here, I don't really care. Know some pressure ratios, and here's the stuff to remember about Unit 2. Okay? If you increase the pressure by a factor of 10, you went up 20 dB. And you'll always remember the picture. This table relates directly to this particular picture here. And never forget. Okay, there it is. That is the most important picture in this unit, relating directly to this table here. Okay? Now, remember this, due to logarithms, doubling the sound pressure levels does not double the dBs. For example, if you double the SPL represented by 20, you don't get 40. In other words, if you had a 1000 Hertz tone at 20 dB SPL and you doubled the pressure, you'd be now at 26. Okay, if you increase the pressure by a factor, now look where I'm going, if you increase the pressure by 2 to 1, you've gone up 6. Okay, if you increase the pressure by 10 to 1, you've gone up 20. That's the same as me showing that over here. If you increase the pressure by 100 to 1, you went up 40. That's the same as showing it here. Okay, and a 2 to 1 pressure increase means you went up by 6 dB. So now let's say you took a 1000 Hertz tone of 40 dB SPL and you added another 1000 Hertz tone of 40 dB SPL. What's your sum total? You should say 46. But what happens if you took a 1000 Hertz tone of 40 dB SPL and a 1500 Hertz tone at 40 dB SPL? The SPLs are the same, but the frequencies are different. Therefore, you only go up by 3. So in this case, 2 different frequencies added together, both 20 dB SPL, the sum total would be 23. A machine in one corner making 90 dB SPL and another machine in the same room making 90 dB SPL. How much do they total? 96 or 93? Well, that depends if the machines are identical or not. If they're identical, the sum total would be 90 and 90 is 96. But if they're not, which you should always assume that they're not, okay, because even if they're identical machines, they're in different areas of the room, so the reverberation is going to make something different. So in this case, 90 and 90, the sum total is 93. And that's what it means when we scroll our way down to this. In real life, you normally are not adding together tones of equal frequency and phase. Now you only go up by 3. And this is an important paragraph. I would star this one. Make sure you internalize this, okay? So that's why I'm saying, so if you have a guy talking at 65 dB SPL, if you had 10 identical guys, you would have a 20 dB increase to 85. But in all actuality, it's going to be 10 different guys because we don't know how to make clones yet. Okay, so if one guy's talking at 65 and now suddenly there's 10 guys each talking at 65, your sum total, you went up by 10 instead of by 20. Just like 3 is half of 6 with a double pressure increase, well, 10 is half of 20 with a 10-fold pressure increase. Same logic, okay? If a person sings in a choir at 70 dB SPL, what's the total dB SPL of a choir of 100 people singing each at 70? Recall, they're not identical. If they were identical, the increase would be by 40 because a 100-fold pressure increase corresponds to a 40 decibel increase. So you'd have 70 plus 40 would be 110. But in all actuality, they're all different people. So your increase is 20. Just like 10 is half of 20 and 3 was half of 6. So your total is 70 plus 20 is 90. All review, make sure you have a handle on that. Also in real life, you're not always adding equal decibels together. You might be adding a bigger one to a smaller one. So they're not only different in frequency, they're also different in intensity. So if they're different also that way, remember this, an elephant plus a mouse is basically an elephant. 50 dB SPL plus 40 dB SPL is basically 50. Okay? Unless, so you're assuming that the frequencies are different, so you're only going to be going up by 3 if you double the pressure, okay? So let's stick with that. We're leaving identical behind. Leave it. But now not only are the frequencies different, but also the intensities are different. You're adding a big one plus a little one. Well, if you've got like 10 or more difference between your decibel levels, basically the addition of the two is just the biggest of the two. It would be 50 and 40 would be 50 point blah, 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 blah. An elephant plus a mouse is basically the elephant. But an elephant plus a tiger, an elephant's bigger than a tiger, and an elephant plus a tiger, well, that tiger's going to add something to the elephant. Okay? So if the sum total between your two decibel levels is less than 10, well, then you're going to start adding something to it of note. Until you get all the way down to 0, when there's no difference between the two, then you went up by 3. Okay? And that's why I showed you this picture here in Unit 2. And I think what we did was we went to, and I think it's this picture here. It's also an important picture, okay? To add 85 to 90. Okay, 85 and 90, they're not 10 dB different, they're only 5 different. So find the difference between the two numbers, 5. Find 5 on the curved line, 5. And then follow that horizontally to the left. And that's the amount of decibels that you would add to the 90 if you were adding 85 and 90. Because remember, 85 is getting close to 90. They're no longer 10 or more apart, okay? They're getting close. So you would add, not 0, not 1, but 1.2. So I guess your total would be 91.2 dB SPL. Stuff like that. Don't memorize. I don't have this memorized. Note that if there's no difference, look where my cursor is, between the two, you're going to add 3 decibels because now you're doubling it. You're adding two things together. Okay, there's something else in this unit that's very important, and that's absolute versus relative dB values. And put a star by this one here. Very important on the midterm. Hearing aids. Input plus gain is output. You've got 2 different decibel values. One's dB SPL and one's dB. dB SPL is always referenced to 0. So what's ambient room noise? 35 to 40 dB SPL. That's relative to the ground of 0, which we defined as the softest it took for a normal hearing human to hear a 1000 Hertz tone at 1 meter distance with 2 ears. You got to know what the ground is to tell if an apartment building is twice as tall as a house. So here you go. All dB SPL values are absolute. We call them absolute because they are related and relative to the ground. Okay? Of what? 0. So what's average conversational speech? 65 dB SPL. What's yelling? 80 dB SPL. What's a lawnmower? 120 dB SPL. Okay, all of those are absolute values. Absolute meaning they're always stipulated in dB SPL, and they are referenced to the ground of 0. And you can't add 2 together like 1 plus 2 is 3, just like we've discovered. If they're identical, if you double the pressure or you add double them together, you're going up by 6. If they're not identical and you add 2 together, you're going up by 3, right? We covered that. So a machine making 90 dB SPL and another machine making 90 dB SPL, assume that they are different, your sum total is going to be 93. And what was that? That was a gain of 3, because 90 plus 3 is 93. So hang on, we did just add decibels together like 1 plus 2 is 3. Yep, in certain situations you can. If you are adding an absolute dB SPL value that's related to the ground of 0 plus a relative decibel value, which is always stipulated in simple dB. Okay, so dB SPL plus dB equals a sum total dB SPL, and that's going to be like 1 plus 2 is 3. So 90 dB SPL plus a gain of 3 dB is 93 dB SPL. But 90 dB SPL plus 90 dB SPL is 93 dB SPL. That's a gain of 3. And in hearing aids, we do this all the time. Input to the sound coming into a hearing aid. Sound coming into the hearing aid mic. So let me pull out a hearing aid here. Sound coming into a hearing aid mic. Sound coming into a hearing aid microphone. The mic is at the top. Sound coming into the mic, be it traffic, be it my voice, whatever, that's the input. That's always dB SPL. Whatever it is, call it X. Plus the gain. What's the hearing aid adding? With the battery and the amplifier, what's the hearing aid adding? And that's always dB, not dB SPL. And then the sum total coming through the tube and into your ear, that's called output. And that's always dB SPL again. Okay? It sounds like a dB SPL again. Oh, not him again. dB SPL again. Okay? So input plus gain is output. And input is always dB SPL, gain is always dB, and output is always dB SPL. So if my input was 50 and my gain was 50, guess what my output is? 100. Okay? I can, C-A-N, can add like 1 plus 2 is 3 if and only if I'm adding an absolute dB SPL and a relative dB. Then I can, and thank goodness that's what we do in our field all the time, because we deal with bags of hearing aids. We're not dealing with machines in different corners of the room. Share screen again. Got 5 minutes left. We're doing good. I've spent most of this stuff on units 1 and 2, mainly for review. Okay, unit 3 is fresher in your mind. The last thing here is dB SPL and negative values. Always remember that 0 dB SPL does not mean no sound. It's simply the softest it took for a normal hearing human to hear a 1,000 Hertz tone at 1 meter distance with 2 ears. If I decreased the pressure by a factor of 10, then you'd have 0.00002 dynes per second, 4 zeros in front. And that would actually be minus 20. Remember, if you increase the pressure by a factor of 10, you go up by 20 dB. Okay, if you decrease the pressure by a factor of 10, you go down by 20 dB. And that's provided everything is identical again. Anyway, enough on that. I'll take that and close it. And now I'll take this and close it. And let's go to our last unit, unit 3. And remember, non-periodic versus periodic. Know what those definitions are. Know what the difference is between line versus continuous spectrum. Put a star by that. Know who Monsieur Fourier was. Know what a fundamental frequency is, the lowest frequency in a complex sound. I'm not going to ask you to memorize what square, triangular, and sawtooth waves are. I just want you to know that they are basically 3 experimental complex waves that show how complex waves can be built to look really weird if you add frequencies to them in just the right way. But don't worry about that. That's just for your own esoteric knowledge. Beats, you need to know what this is. You add 2 tones together that are very far apart, you'll get 2 distinctly different frequencies. But if you're adding 2 tones that are really close together in frequency, you're going to hear beats. Whoa, 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 whoa. And know that the beats will occur at the rate of the differences between the frequencies. They will occur at a rate of F2 minus F1. So if I gave you 1001 Hertz and 1000 Hertz equal intensities, you're going to hear 1 beat per second. 1002 Hertz versus 1000 Hertz, give those 2 together, you're going to hear 2 beats per second. Enough on that. Next. Oh, look at this. You're getting that opposition and resonance and resistance all again. Just to hammer down the fact. Remember, remember, remember. All of this section. Okay? Impedance and resonance of any object which can be said to act as filters. Put a star by this one. Okay, common types of filters. Looky, looky, looky. Put a star by transient and turbulent. Because now we're getting into types of noises. Turbulent noise is continuous, like a fan or an air conditioner. Transient is like a door slam. Okay? 2 different types of noises. And they occur in speech too. And break down the frequencies of speech. Vowels are louder, lower, tonal, okay, and they are not, okay, and consonants are softer, higher frequency, and they are non-tonal. They are noises. And then you've got mixtures in between. So if I'm saying E, vowels. Even the letter M. Mary, Bob, okay? Anything using the larynx is louder, lower, and tonal. High frequency sounds are made with the lips. Consonants. They are higher pitched and they are noises. And consonants have 2 types of noise. They might be turbulent, like an S or an F, or they might be transient, like a T or a K or a P. Okay, so turbulent, transient, apply those to the consonants. And then last of all, go into your notes here and break it down and even look at the frequencies of speech in terms of spectrum. So when you're looking at a spectrum here of speech, let's see, do I have a spectrum of speech even on here? I should. Okay, you got all kinds of good stuff on here. Here, spectrum of speech. Okay, vowels are louder, lower in pitch, and consonants are higher frequency and softer. And in your notes, we really broke it down, and I would focus on this and make sure you got this. Look at this table here very carefully. Right here. Okay, there you go. Vowels, voiced consonants, unvoiced. Unvoiced is the highest in frequency. Vowels are the lowest in frequency. Unvoiced, if you took the letter F and you put a voice in it, you got a V. If you take the letter S and you put a voice in it, you got a Z. If you take the letter P and you put a voice in it, you got a B. The pop, bop, pop, bop, fob, vob, fob, vob, sob, zob, sob, zob, okay? Church, jerk, okay? Church, jerch, or keep, geep, a G, kind of neat. And then we finish that unit with all about helium speech again. Here we are uniting things covered in Unit 1 and Unit 3. Okay? And make sure you read this stuff. Put it together. Hook it together like Granny Groove makes a big blanket. Weave it together. Weave 120 and 110 together. Hook them together. Crochet them together. Okay, all of this because you're crossing over even now into anatomy. Presbycusis is the high frequency hearing loss in an elderly population, extremely common. In acoustics of speech, vowels are louder than the consonants. Vowels are normally heard more loudly than the consonants. With presbycusis, the audibility of the consonants is compromised even more. Speech really sounds like a mumble. It almost is going to, your presbycusis, high frequency hearing loss, is going to even act intelligently, like analogically, it's going to act like a low pass filter. It's cutting off the high frequencies of speech. Okay, it's not it's not doing it like a filter does with mass and stiffness. Please don't think that. But in an analogous kind of way, you could think about presbycusis as a low-pass filter. It's letting the lows get through. So the elderly person, the high-frequency resonance of the ear canal is no longer enough to help aid the audibility of consonants because they've got high-frequency hearing loss. And when you look at that as a picture in your PowerPoint notes, and you go to the end, you can see this. Here's the picture. Here's your ear canal resonance that I'm tracing, where it would normally be 3,400 hertz, but because the ear is made out of flesh and bone, that resonance is spread over a range of frequencies. And now you can see the X's and O's, and look at the values here. It starts at about 1,500, ends past 4,000, and the peak is at around 2,700 hertz. Remember, remember, remember. And the decibel value of this resonance would be about 20 to 25 right over here. So if you called this 0, this would be about 20, 25. And this person has a high frequency hearing loss, represented by the O's being the right ear and the X's being the left ear. And the person can hear the low-pitched sounds of speech but cannot hear the high frequency consonants. Presbycusis. And that's where what we're talking about here. Last thing, resonance of the outer ear canal. There it is yet again. Okay, so these are the salient and high mark points that I need people to look at in terms of the physics acoustics. There we have it. I will generally sign off now. D would be for done. Slightly longer than average Zoom session. No matter, doesn't matter. It's called review. So I'll be sending out everybody an email to make sure that people watch this Zoom session, okay? Anyway, I will stop recording and end the session. Good luck on the midterm. Hope you sail and whiz on through. Live long and prosper.